One of the most dangerous threats to our nation's security is the possibility of attack by high-speed enemy bombers armed with nuclear weapons. These bombers can strike at supersonic speeds from many directions and altitudes to confuse our defense and delay the dispatch of interceptor weapons. At radar stations which blanket our country, at distant early warning stations, and other outlying radar observation posts, the enemy aircraft would be detected and tracked on huge plotting boards. But even skilled men, unassisted, cannot work fast enough to track mass high-speed raids, to record them by hand on a screen, compare them with friendly flight plans, mark and erase, plot and analyze, while aircraft armed with nuclear bombs bore in from many directions. In a mass raid, high-speed bombers could be in on us before we could determine their tracks. And then it would be too late to act. We cannot afford to take that chance. It is to meet this threat that the Air Force has been developing SAGE, the semi-automatic ground environment system, to strengthen our air defenses, giving it a speed of operation sufficient to defend us against mass jet bomber attacks. My name is Colonel John Morton. I'm one of the officers associated with the North American Air Defense Command. I want to tell you something about this complex new defense system we call SAGE, how it came into being, what it is, and why the Air Force feels it's vital to our defense. With the advent of supersonic jet aircraft, it became apparent that the manual air defense system, so long in use against the threat from slower planes, could no longer provide adequate protection. The vast network of radars, constantly pouring information into the manual control centers, would need mechanical help if the threat from mass raids was to be met. To develop such a machine, the Air Force called in the Massachusetts Institute of Technology, where mathematicians, physicists, and other scientists set to work on the task. Soon it was decided to establish a new research center, known as the Lincoln Laboratory. Here, the most advanced technology was applied to all aspects of the problem of air defense. Of particular value was the use made of an already existing electronic computer, Whirlwind 1, the Navy-financed digital computer, a remarkably rapid computing machine. It quickly proved that computers could be used to process large quantities of air defense data and to do it at high speed. Out of Whirlwind 1, after additional months of research and development, evolved a new electronic computer, larger and much faster. This new computer, built to become the nerve center of a defense network, is able to perform all the complex mathematical problems involved in countering a mass enemy raid. It receives the information, stores, or utilizes it immediately, calculates speed, altitude, and course of aircraft, and enables operators to identify the planes as hostile. Analyzing all of its information, the computer in a few seconds gives a complete picture of the attack and then guides manned interceptors or missiles to the target. To utilize the amazing capacity of the computer, air defense planners designed the SAGE system, a network of geographical defense sectors covering the continental United States and extending into Canada. Each sector has as its focal point a computer installation known as a direction center. A group of sectors comprise a NORAD division, where the key point is a computer installation called a combat center. Combat centers are headquarters for higher echelons of command, integrating the individual sectors into a centralized defense system. A typical sector of the SAGE system operates in this way. Information is fed to the direction center from many sources. Long-range radars which constantly sweep the skies of our far-flung frontiers, probing high into the atmosphere. Airborne early warning planes of the Air Force and Navy, patrolling the oceans hundreds of miles offshore, carrying electronic eyes far beyond our borders. Radar picket ships of the Navy, which form a mobile frontier on both oceans, always on watch. Gap filler radars, which plug up any empty spaces in our land detection system between the long-range radars. Texas towers, strange-looking radar sentries on stilts above the shoals along our coastlines. Air movement information services, reporting the movements of friendly aircraft for comparison with unknown tracks. Even information about the weather. All this information is analyzed in the direction center, stored on memory cores or drums, or utilized immediately for defensive counterattack. From the direction center, commands go to intercept aircraft at fighter bases, fueled and ready for immediate takeoff. Commands go to ground-to-air missiles, Bomart bristling on launchers, and to Nike batteries dug in around our cities with trained crews ready for instantaneous action. The design of the complex SAGE system was a tremendous step forward in air defense. But the task of actually constructing the system, manufacturing, installing, and testing its associated electronic equipment, and building the continent-spanning communications network presented a tremendous challenge to the military and to industry. Many organizations, small as well as large, were called upon to make their contributions to this effort. Lincoln Laboratory was given the task of designing the SAGE system, pursuing research and development assignments, and providing the initial computer programs. To IBM went the job of designing, manufacturing, installing, and maintaining the high-speed electronic computers, the largest and most complex computers ever built. The System Development Corporation was selected to work with Lincoln Laboratory in the preparation of master computer programs, to continue the production and revision of programs, and to develop training methods for maintaining Air Force crews at high proficiency in the use of this system. Burroughs Corporation was given the assignment of manufacturing, installing, and maintaining the electronic equipment required to process radar data for transmission from long-range radar sites to the computer at each direction center. Western Electric Company was selected to assist the Air Force in coordinating and managing the entire effort to assure its completion according to schedule. In addition, it was assigned the responsibility for the design and construction of direction and combat center buildings, assisting the Air Force to develop basic communications plans, and testing the system to assure that Air Force operational requirements are met. Supporting these prime contractors and others are hundreds, if not thousands, of small companies supplying goods and services. This entire effort is guided by the Air Force SAGE Project Office, who maintain close control over the project and provide the leadership and decisions needed to meet the exacting schedules. Executive responsibility for this project is vested in the Air Materiel Command. The SAGE Project Office is comprised of representatives of this command, as well as of the North American Air Defense, Air Research and Development, and Air Training Commands. Through the SAGE Project Office, the Air Force and industry cooperate in the great effort needed to make SAGE a working defense system. SAGE is off the drawing boards. It is being rushed to completion into concrete buildings, buildings to house vast networks of wires and tons of delicate electronic equipment. As soon as SAGE installations are completed, they are turned over to the air defense system. Here at the McGuire Air Force Base in New Jersey, the first SAGE installation to become operational is being accepted by the Air Force. Others are following rapidly according to schedule. Direction centers are the nerve centers of the SAGE system, built for one purpose: to house the huge computer and the men who will use it to continually monitor the air situation and, if necessary, direct the air battle. The computer constantly calculates and recalculates the position, course, and speed of all aircraft seen by our radars, and continually presents this information on scopes, which are installed in rooms illuminated by dim blue light, making the displays easy to read without fatigue. Here in the air surveillance room, all tracks are monitored. In the identification room, questionable tracks are identified as either friendly or hostile. In the weapons direction room, hostile tracks are evaluated for threat. Weapons are assigned, and the air battle is directed. And this is the command post, where the sector commander supervises his area's air defense activities as they are displayed to him and his staff on the large screen. He coordinates these activities with those of adjacent direction centers and communicates with Air Division headquarters. Thus, an individual direction center performs its portion of the air defense task. To make the direction center completely self-sustaining, it is provided with its own powerhouse containing large diesel-driven generators, air conditioning equipment, and cooling towers required to cool the thousands of vacuum tubes in the computer. Each sector has an extensive telephone system, which forms the connecting links through which the computer receives and transmits data to and from outside locations such as radar sites, weather stations, interceptor bases, missile sites, and the many other facilities which are needed for the operation of the air defense system. This telephone system also provides communication between personnel in the various SAGE facilities. All the equipment in the center, the thousands of delicate tubes, the miles of wiring, and the other thousands of complex components must be carefully maintained and constantly checked for maximum reliability. Pluggable units make maintenance simpler, permitting rapid isolation of difficulties and speedy replacement of units. 24-hour-a-day reliability is assured by installing the computer in pairs, both computers storing and processing data continually, one on duty and the other on standby. Should a direction center be damaged or destroyed, its air defense task would be taken over by adjacent direction centers. Each direction center has a training and battle simulation room. Data inserted in the computer simulate enemy attacks so that men and equipment can be evaluated and skills developed. The mock attack information is also displayed in the air surveillance room, where operators track the aircraft. In the identification room, the enemy planes are identified. And in the weapons room, mock interceptions are made. Thus, men and equipment are readied and trained for battle. Combat centers house the men and equipment which receive and evaluate information from the various direction centers in the division. The information is relayed to the NORAD division commander and his staff so that they can allocate forces, evaluate the various threats, and supervise the entire battle in their division. From design through operation, the SAGE system is an eminent example of military and industrial teamwork in action to strengthen our continental defenses. Now, let's see how SAGE would operate in case of attack. Let's suppose an enemy launched a surprise attack with high-speed aircraft intent on destroying our great cities. The long-range radars which constantly scan the skies detect all planes in flight. The information is flashed electronically to the direction center, where the computer instantaneously makes the necessary calculations and displays its findings as tracks on the scopes at the consoles. In the air surveillance section, tracking operators monitor all traffic in the sector and quickly relay unidentified tracks to operators in the identification section who determine that the tracks are hostile. An alarm sounds in the weapons direction section. The senior director and senior weapons director size up the threat using all the up-to-the-minute information displayed before them on the scope. The defensive weapons they might use are Bomark and Nike, which are installed around the major cities, symbolized by the smaller circles. The protective range of these missiles is shown by the larger circles. Interceptor air bases, there are 3 of them here, are symbolized as small airplanes with letters designating their locations. The hostile track appears in this manner, with symbols which tell important facts. In this case, U means no interceptors have been assigned to the track. The second U, no ground-to-air missiles have been assigned. H, the track is hostile. G, tracking is good. P, the track is not yet assigned to a weapons team. And M means the track is at medium altitude, that is between 10 and 30,000 feet. A137 is the number assigned to the track. The vector line shows the direction and by its length the speed at which the enemy is flying. To determine if interceptors should be used against the hostile, another display is obtained. The squares indicate the intercept points for aircraft from 2 of the bases. O20M and O15M indicate the time to interception in minutes. I-200 and I-150 indicate the distances from air bases to intercept points. On the basis of this information, constantly supplied by the computer, the track is assigned to a weapons director who decides that interceptor aircraft should be sent against the enemy. Immediately, the weapons director assigns the control of the intercept to an intercept director, whose situation display shows him that fighter craft have been scrambled. The situation display also indicates that the interceptors are assigned to track A137. I indicates interceptor aircraft. G, that tracking is good. 1, the number of the controlling weapons director. 2, the number of the intercept director. A vector symbol indicates the heading of the fighters as they fly toward the point at which interception will take place. RL-15 is the intercept flight code number. Thus, the intercept director has the information he needs to direct his portion of the air battle. And the battle begins. At 28,000 feet, the bombers speed toward their targets. But jet interceptors roar to the attack, guided by electronic impulses received directly from the computer, supervised by the intercept director miles away. Now comes the test. Were the calculations correct? Were our judgments right? With weapons rushing toward each other faster than the speed of sound, the slightest error can mean failure, and bombers free to strike with nuclear bombs. The console display shows the intercept weapons approaching, and the battle is joined. The fighters lock on target, and rockets are fired. The battle is over. The enemy destroyed. But one important task yet remains for the computer: to guide the interceptors safely back to their bases. A successful mission has been performed by SAGE, the air defense system with the electronic eyes and the incredible speed necessary to counterattack swiftly against an enemy. But we know that time does not stand still, that new and more powerful weapons are being developed, which makes the job of defending our security ever more difficult. The SAGE system provides us, on the North American continent, the finest possible air defense against attack by manned bombers, the number one threat of today, and quite a few tomorrows. But even now, as SAGE is rapidly being installed across the country, scientists, such as these at Lincoln Laboratory, are continuing their research to meet the threats of the future. Many of the techniques of air defense used in SAGE today, the high-speed electronic computers, for example, will undoubtedly be the basic elements of future systems to be developed in your defense. One of the most dangerous threats to our nation's security is the possibility of attack by high-speed enemy bombers armed with nuclear weapons. These bombers can strike at supersonic speeds from many directions and altitudes to confuse our defense and delay the dispatch of interceptor weapons. At radar stations which blanket our country, at distant early warning stations and other outlying, giving it a speed of operation sufficient to defend us against mass jet bomber attacks. My name is Colonel John Morton. I'm one of the officers associated with the North American Air Defense Command. I want to tell you something about this complex new defense system we call SAGE, how it came into being, what it is, and why the Air Force feels it's vital to our defense. With the radar observation posts, the enemy aircraft would be detected and tracked on huge plotting boards. But even skilled men, unassisted, cannot work fast enough to track mass high-speed raids, to record them by hand on a screen, compare them with friendly flight plans, mark and erase, plot and analyze, while aircraft armed with nuclear bombs bore in from many directions. In a mass raid, high-speed bombers could be in on us before we could determine their tracks. And then it would be too late to act. We cannot afford to take that chance. It is to meet this threat that the Air Force has been developing SAGE, the semi-automatic ground environment system, to strengthen our air defenses.